Good morning. I hope the weather is nice where you are. I'm currently admiring the gently wet British weather out of my window. It's a good reminder to remain indoors. The image that you are seeing somehow vaguely fits with this idea of paradigms lost. This is a picture I took last year in Pripyat in the Chernobyl exclusion zone in Ukraine. And yes, you can visit a radioactive world disaster site and buy mugs. So this is a genuine sample there. The coffee, however, is not radioactive. That's my responsibility. So what are we going to talk about? We're going to talk about a bunch of stuff here. We're going to talk about paradigms lost, paradigms regained, programming with objects and functions and more. I want to focus on a number of different aspects here. The challenge for me is that I actually run this as a one-day kind of seminar. And so I did the major mistake of trying to condense that. That was my first draft. I threw that one away because you can't take one day and turn it into 1 hour with any success. So I inverted the whole thing. I've turned the whole thing inside out and basically said, right, let's start from scratch. We'll take a different line through this. So a little bit about me. My name's Kevlin Henney. I don't actually have an at in front of my name, but my name is sufficiently unique that I can get away with it. I've written stuff on patterns, and I've have an interest in architecture in the software world. Very much, really, my interest in patterns is how do people think? How do people organize things? A lot of people think of patterns as just a catalogue of interesting ideas, and it's like, that's not really it. There's something much deeper. There is a thinking model that is profound, and we will actually see relates to paradigms very strongly. I'm also interested very much in the detail of code and practices. So 10 years ago, I published this book, edited this book, kind of crowdsourced open source book, 97 Things Every Programmer Should Know. Most recently, myself and Trisha G published 97 Things Every Java Programmer Should Know. A very different focus in that sense, kind of like 10 years on. Specific language takes everything in a very different direction. And that was fun. It's nice to do something during lockdown. But that's not why we're here. Let's talk about this. Paradigms, the P word. In fact, it did actually get known one place I worked in the early 90s as the P word, because paradigm was being mentioned so often, because people were starting to talk about, let's move to objects. And up to that point, we've been doing a lot of procedural programming. And people talked occasionally about modularity, proceduralism. Functional programming was an academic dream. Occasionally logic programming. Whenever you brought that up, somebody would say, oh yeah, I did Prolog at university, and that would be it. That would be the end of the logic programming conversation. But most code was being written at that point in C, variants of Pascal, Fortran, all this kind of stuff, variations of BASIC. They were never a pure procedural paradigm, but they were variations of it. But at this time, people were talking objects, late 80s, early 90s. This was when it was coming in. And the word paradigm started raising its head. Now, what is interesting is we can actually get a point of origin for the use of the word paradigm in programming. It's this guy, Robert Floyd. He was involved in a lot of thinking in the 60s in particular on formalisms. If you're familiar with Tony Hoare's ideas, in fact, Formal Methods owes this man a great debt. Tony Hoare's ideas of like a precondition, an action, and a postcondition for reasoning about code, which these days we see reflected in behavior-driven development, given, when, then. It's exactly the same three aspects. And Tony Hoare acknowledges this very, very clearly and explicitly and openly. That's actually based on Robert Floyd's work. So he received the Turing Award in 1979. And he talked about the paradigms of programming. And he adopted the term paradigms based on the popularity in the 60s of Thomas Kuhn's Structure of Scientific Revolutions. If I had thought about this, I would go and grab my copy, because one of the great things about being at home, let's look at the positive side, is that I can grab books that I have and show them to you. But yeah, that one's kind of in the other room. What is interesting is before 1979, people didn't talk about paradigms. 1979, they started using the P word. You can see this in the 1978 Turing Award winner, John Backus, who spoke about functional programming. His Turing Award paper and speech, he only talks about the functional style. 1 year later, everybody's using the paradigm word. So paradigm, let's talk about the word paradigm. Oh, good grief. I mean, you know, as if you didn't already have enough trouble with English spelling, here is a word that has a silent G, but only sometimes, because it's paradigm. But when we are talking about paradigms or relating something, we may say that something is paradigmatic. Suddenly the G rears its ugly head. For that, we totally blame English. But if we look at the origin of the word, we see down the left-hand side, we can see, oh, okay, it's Greek. Paradigma is ultimately where it comes from. It means a pattern. It means an example. Oh, pattern, that word. An example, something to follow, an archetype. It's very interesting. But we think we understand what we're talking about when we say paradigms. When you drop that into a conversation with developers, often people talk as if they are pursuing a single paradigm. Which one is better? The one. You know, it's Neo, it's the Matrix. We are after the one. Actually, Robert Floyd's thesis, the whole point of what he was trying to talk about, is I believe that the current state of the art of computer programming reflects inadequacies in our stock of paradigms, in our knowledge of existing paradigms, in the way we teach programming paradigms, and in the way our programming languages fail to support the paradigms of their user communities. He's talking about this as a plural. He doesn't want the one true paradigm. He says, you have different problems, you need different shapes of solution, and these will not all be the same shape. There is no the one. And so what is interesting there is exactly what he said 40 years ago. I would like to repeat here. The moment we find people pursuing or obsessed by the one paradigm, yet when we look more closely at our languages, we find that most of the languages that are in current use do not support a paradigm. They are a blend of paradigms. Paradigms do not have these they don't have boundaries. You know, you are suddenly leaving the procedural quadrant and now entering the functional sector. It's not like that. You know, you don't check in your state mutability at the boundary and that's it. There's a hard distinction and you move from object into functional as if there was no distinction. And in fact, I've heard some people say, oh, there are only 2 or 3 paradigms. It's like, oh, I've got really bad news for you. Here's the paradigm map as of 2005, according to Peter Van Roy. And I would actually highlight that he's missed out a whole bunch I can think of straight there. But this is a good analysis, and he's broken it down along a number of axes with separations, Turing completeness or not, how we relate to state, and he's banded things and showed relationships. So what we're saying here is this is a good first stretch at a paradigm map, but actually we can see there are things missing. We have more examples and that we can throw in. More things that are in between in the spaces, as it were, rather than sitting comfortably inside boxes. So one of my favorite quotes, Émile Auguste Chartier, nothing is more dangerous than an idea when you have only one idea. I love using this quote because it's always a reminder when we come to design thinking, programming style, or even life. That we tend to get fixated, we get locked into one thing. And the whole idea is challenge yourself. And we can actually generalize this in software. Nothing is more dangerous than an IDE when you have only one IDE. And we also see this in particular. Nothing is more dangerous than OO when you have only one object. And for many people, it's just like, oh, object orientation, you mean the singleton pattern. It's just like, no, we absolutely do not mean the singleton pattern. You know, that's a failure mode. That's not the bit we're putting forward and saying, please follow this. This is good. We're saying this is the bit you don't want to do. But there is an important point here that we often pursue paradigms not because of the problems we're trying to solve, not always because of the nature of our languages, but sometimes we want something better. We've become uncomfortable. A paradigm has become, let me put it this way, a lot of what people are doing and calling object orientation, it's not what I was taught. It was not the promise, but that happens for every paradigm. I see a number of well-meaning but very naive people jumping onto, having dealt with functional programming for quite a long time. I love the way people go like, oh yeah, functional programming is the answer because OO is all singletons and managers. And it's like, no, really, that wasn't the idea. What does the enterprisation of functional programming look like? The enterprisation of functional programming is already happening. We see functions called function. We see people using hybrid languages and saying, I've got this really big, super long function or method or whatever. And it's just like, it's because I'm doing functional. It's like, honestly, some data abstraction would really help you at this point. And we know what the failure mode of functional programming is, what that looks like. The failure mode of object orientation is managerialism. The failure mode of functional programming is called procedural programming. In other words, we have pragmatic side effects. Yeah. So when people use the word pragmatic, it normally means not. So when people do pragmatic agile, it's not agile. When people do pragmatic TDD, it's not TDD. When people are doing pragmatic functional programming, it's not functional programming. They have pragmatic side effects and pragmatic others. So we're already seeing this in some effect. That's not to diss FP at all. FP is really quite significant in the landscape, but it's our hopes that are being surprised by. We're being surprised by. So what I need is one idea that I'm going to run through all of this. So we're going to talk about stacks. So this is the 7 Magic Mountains outside Las Vegas. Back in a world where we used to be able to travel. I was in Las Vegas last year with the family, and this was much more interesting than the fake Eiffel Tower there. Stacks are very common ideas. We find them. Here's a stack of books that's all about objects. Psychotherapists are utterly obsessed with the concepts of objects. We also find that we talk about full stack developer. Stacks are obsessed. People are obsessed. In fact, if you want the best kind of full stack developer, you need them to be passionate as well. Although I find that when I look at what people mean by actually full stack development, it's kind of small. Their universe is apparently the full stack is front end and back end. My background is that I used to work in infrastructure, systems programming, and middleware. And for me, what most people call full stack development is somewhere up there. My bit of the stack is completely neglected. The other area I guess I'm interested in is the other aspect. How do we do products? What is the effect on society? It turns out the stack is surprisingly deep. And what we call full stack is a tiny squinchy bit in the middle. But that's not the stack we're going to talk about. I'm going to talk about data abstraction. This is my perfect excuse to use upside down A's and back to front E's in a talk to commercial programmers. There exists a type T, this is generic, such that for all stacks, and then I offer you a Cartesian product with a series of functional mappings, some of which are partial. So popping a stack does not always yield a stack. Sometimes it's not an allowed operation, popping an empty stack. So and getting the top of a stack is not always legal, because if it doesn't have a top, the way that we frame the types here, we're going to say that's not always true. So what we're talking about here is abstract data types, ADTs. So let's start there. ADTs, abstract data types. We have, this is an idea from the early 70s. Specifically, this is Barbara Liskov. And while we're talking about Turing Award winners, she was the winner, I think, in 2008, 2009. I could be off by one. Her work in programming language design was really quite significant, quite important. If you are using a language that has an exception handling mechanism that looks roughly like try catch, try except, or whatever, that comes down to the language work that she did in the 1970s, the CLU, CLU language. But she is one of the key people involved in this whole idea of ADTs. This is from her 1974 paper, Programming with Abstract Data Types. Now, what's interesting here, she says, an abstract data type defines a class of abstract objects, which is completely characterized by the operations available on those objects. A program is concerned only with the behavior of which that object exhibits, but not with any details of how that behavior is achieved by means of an implementation. And a lot of people are going like, oh, okay, yeah, cool, right, yeah, we do this all the time. This is classes, okay? So if I throw this one at you in C#, then I've got some private implementation, which, as Liskov says, we're not interested in, characterized completely by its public operations. Its public aspect is push, pop, depth, and top. Let's keep it really simple. And I'm going to make pop a pure pop. Actually, there are reasons I might come to later why I've done it this way. But I'm going to keep it really, really simple. You want to find out the value that you're about to pop? Ask for the top. That's it. And I can implement it. I can implement it in C# using the standard .NET generic collection list, which is basically a resizable array, vector in other languages, array list in others. So it's based on contiguous memory, and I can push and pop freely. I've got my exception behavior nicely characterized there, a number of forwarding operations. So this is stack implemented as a wrapper. And I've chosen a particular sensibility here. I have decided that the head of the stack will be the 0th element of the list. And if you look through there, you will see that there it is, element 0, insert 0, that's my push. So we've got a really simple and pop, remove out 0. But I could equally well do it the other way around. And actually it's marginally more efficient to do it the other way around, that push appends at the back. That's what add does by default, but it means that I remove from there. So I count backwards effectively. Or I could use a linked list, and I could take things from I could treat the top as the last element, or I could treat it as the first element. Now notice all of these variations have been done without any appeal to a difference in terms of the perceived semantics. But this is not what Barbara Liskov was talking about. In many of our minds, when we read a lot of stuff on ADTs, particularly if you come through the object route, and that's been your main exposure, you will think, oh, yeah, that's what I'm doing. And it kind of is, but it's not the whole story. So this book, Theory of Objects, I'd love to say I've read it. I've read the first section. I think there are 5 or 6 sections. I've read the first section. The first section is in English. The remaining 5 sections are in Sigma calculus. And if you are struggling at any point to sleep at night, I strongly recommend some of those sections. Not for me. There are people out there who have far better appreciation of reading formalisms. But the first section is gold. Absolutely really good clarifications. This book was published in 95. And the point that Abadi and Cardelli make, they say, object-oriented programming does not have an exclusive claim to all these good properties, those properties of data abstraction and so on. Systems may be modeled by other paradigms. The resilience that we've just been describing can be achieved just as well by organizing programs around abstract data types. Treat it as a separate concept. The whole private-public, keep your data private type thing is not unique to object orientation. But for many people, particularly when they've come from a regular procedural background, whether it's from scripting or from C, when they see objects, that's their big enlightenment. It's the encapsulation. That's the thing they associate primarily in their mind. They say that paradigm is about that. Actually, it's not. There's actually a bunch of paradigms that all share this. So as Abadi and Cardelli say, organizing around abstract data types independently of taxonomies, what they're referring to here is class hierarchies and type hierarchies. In fact, data abstraction alone is sometimes taken as the essence of object orientation. So this is like category substitution that we do. But I've been mentioning C, so let's talk C. You can do ADT programming in C. In fact, that's where I started doing ADT programming. Although when I did it, I thought I was doing a kind of like bankrupt version of objects. Actually, I was doing ADT programming. I feel much better about it historically. I can forward declare. I can forward declare a structure. I can. I don't have to use it. I'm going to use a name convenience, type def, and put a stack. It's just going to be a stack. So I've now forward declared it. It's incomplete, but I can still define operations on it. I can still declare, go ahead and say I can have a new thing. I can get rid of it. I can do push, pop. I can find the depth, and I can ask for the top. So I'm going to bind the type much more specifically here. There's no concept of genericity. And I really wasn't in the mood to use void pointers this morning. Honestly, it's towards the end of the week. Why would I give myself that pain? So I'm going to just make it very specific and make it about strings. So I can do this in C. It's not necessarily a common style in C, but I know that whenever I've encouraged people to do this, there have been benefits. And when I did it, I found huge benefits in separation in terms of reasoning, but also build times and other aspects. But it is a capability C supports, even though it doesn't present itself as an ADT language. It is a capability it supports, but it's not its principal home territory, if you like. There are languages, however, for which this is a prime aspect. So this is modular 2. Again, if I'd thought about this, my modular 2 book, I can actually see off to one side. What I've done there is I've created an opaque type. Type stack is offered there, but it's not defined. It's kept that definition is kept separate. I can create it, delete it, push, pop, depth, top, all of these usual things. But modular 2 has something else. This is the idea that we don't generally end up with languages that are unique, support only a single paradigm. They normally bring in something else. As the name Modular 2 suggests, it's all about the modules, modular programming. If you like, modularity is partly orthogonal to how we organize our data types and our procedural aspects of code. It's an organizing principle we find in languages as different as Python and Haskell. And Haskell we regard very much as the epitome of functional programming thinking. And Python, although it is an object-oriented language, its default mode of usage is a kind of a light procedural with hints and a light sprinkling of functional, and it supports a modular concept. Now, I can't actually, strictly speaking, do full modular programming in something like C or C++. C++ 20 has modules, but they're kind of different, and I'm not going to get into that. The modular programming idea that I deal with headers and so on in languages like C, the module does not have identity. The key idea that we get with Python and with Modular 2 and languages like that, going back to Ada and so on, is that these languages, the module has identity. You can name it. You import things from it. You have you don't just have concepts of public and private, but you have a namespace concept built into the structural unit. It's part of the language. Now, that, of course, itself is not a new idea. Many people will date modular thinking to the 1970s. I don't know, we take a Wayback Machine all the way to the 1960s. We go back to the NATO Software Engineering Conference in Garmisch in 1968. Actually, there was an awful lot said about this. Define a subset of the system which is small enough to bring to an operational state. This strategy requires the system be designed in modules which can be realized, tested, and modified independently. What is important here is that modularity was being proposed and discussed and reasoned about. As you can tell from the phrasing, it was being offered as a way of thinking about or a methodological approach. As you can see, he offers a recipe to find a subset of the system, this strategy. He's talking about a way of development with respect to a team and so on. So in other words, modularity fulfills a human need in that sense. The reason many people associate modularity with the 1970s is because of David Parnas, who basically came up with a much clearer view of and how should we do our modules. If you like, modularity was an idea from the late 60s. People started reasoning about breaking their code into chunks, and chunks that were not simply subroutines and functions, but chunks that cohered together. But there was discussion about, and why do we make them modules? So Parnas's 1972 paper on the criteria to be used in decomposing systems into modules, we propose that one begins with a list of difficult design decisions or design decisions which are likely to change. Each module is then designed to hide such a decision from the others. Wait a minute. I see. Like changing the implementation, like I just did with the stack. I've got it. So notice here that we've already noticed that we're able to blend. There's a little soft boundary between some of these paradigms, and some of these live together. But the ideas are matured. But these days we often look at something and we go, got it. You mean objects. It's like, well, not just objects. There are other aspects. Data abstraction is something you can do in multiple languages. Modularity without data abstraction is something we can do in multiple languages without needing to tie ourselves to a specific paradigm. But back to this idea of hiding decisions from other people. Well, I did it with C#. I want to show you, if I take this as C, I can go and add a little bit of extra dressing around it so that it will also compile. I've been very careful that this is actually C and C++. Yeah, C was originally kind of like and C89, or I say C90. There was a strict subset relationship, and that was Bjarne Stroustrup's intention, but with a few of the options taken out. But the subset relationship was really strong. As each of those languages has evolved, C99, C11, C17, C++, 98, 11, 14, 17, 20, keep counting. They've diverged. The common subset is proportionately smaller, but what I've offered you on screen here is in that subset. And I can elaborate this in a .c file. I can offer you a full definition of what do I mean by stack. I've got a struct here, and I've got the joy of pointers to pointers, and I've got information there, and everything's doing what it should do. But I can also implement it in C++ and link that in. And the point there is that this is a link time concept. And that was actually something that you found in a lot of the early modular thinking and early ADT thinking, the idea was not to deal with substitutable types with respect to an interface at runtime. The idea was very much a compile time or link time change. Whereas in many of the languages we deal with objects, if you change the private section, boom, that sets off a ripple in your build. The idea is that if you are working in a language that truly supports modules and abstract data types, then if you change the implementation, it does not trigger a huge build. It is merely, it's a recompilation of that module and everything else just links in. And if you're working in a dynamic environment with DLLs or shared objects, that just comes in. So in other words, there's no difference. It's a minimal change paradigm. That is not true of many object systems that we have now. So there are other aspects that come out of that. But since we're time traveling, let's go back to the early 70s. Structured programming. This was the kind of prevailing, as it were, organizational model or good practice procedural programming that people were talking about. And this book, I said early 70s, but strictly speaking, it involves a collection of essays from Ulla Johan Dahl, Edgar Dijkstra, and Tony Hoare from kind of late 60s onwards. It's not really written as a single book. It's really actually a set of essays authored or co-authored by each of these individuals. But they make a really important point about one of the most key ideas. We can actually say within procedural programming, there is a sub-paradigm that we can call block-structured programming. Not every language that is procedural has block structure. C and C++ are of that heritage. Basically, anything with curly brackets is of that heritage. Anything with begin and end is of that heritage. Not everything is, though. The languages of that time, things like Fortran, don't follow that. We also see that in that's not just an old thing. Languages like Python, they're not actually strictly speaking block structured. They don't have the concept of block scope. Although they allow nested procedures, and there's clearly a strong sense of indentation, the concept of the block does not strictly exist. And so, yeah, that's not necessarily a disadvantage. You have languages that pretend to be block structured. Classic JavaScript is an example. It has blocks, but it totally disrespects what they mean. Modern JavaScript is a little tighter on this, but still allows you that old school fluidity. But the observation in hierarchical program structures that Dahl and Hoare wrote, they made this observation: one of the most powerful mechanisms for program structuring is the block and procedure concept. That idea of being able to, and this is something that many languages lost. So C lost the block and procedure concept. It kept the block, but it did not allow you to embed procedures within the block. That was something that was lost. Pascal kept the nested procedures, but did not allow you to nest data within blocks. So they each kind of took a different path. But let's go all the way back. I'm basically going to look here, old school, begin end. This is an Algol 60 derivative, so algorithmic language 60, Algol 60. Really, this is the language that gave us BNF. And it is the language that really launched block structure. Obviously, many languages later decided that begin and end, that's way too much typing. We're going to put curly brackets or round brackets or some variation of brackets in that place. This is a slight extension to it. I'm going to take the concept of a book. We'll discover what a book is in a moment, or rather what it could be. I'm going to make it, I'm going to have an array of reference to books, and the number of books is 1 to some kind of capacity. And we're going to have an integer count that we've got there. So just as a point of history, Algol is the language that put the type name at the front and then the variable name. This is what C picked up on. So this is the language to blame for that practice. I can go ahead, I can initialize count to 0, but I can also nest procedures within this. So the point is that blocks are recursive. Within a block, you can contain all of the ingredients of a program, including more procedures. Procedure for push and pop, and is empty, is full, depth, and so on. I have to put in the is full because it's a bounded. We are limited. We don't have resizable arrays in this era. It's limited to whatever capacity is. But what is interesting about this is that I've just kind of told you something that you probably already know, but you're perhaps translating it into curly brackets or going, oh, I can't do that in the language that I'm using because I'm not allowed to nest the procedures, but maybe I could do something like it. We have seen some languages reclaim the idea of nested procedures. I've noticed C# did that a while back. And you can kind of fake it in C++ with kind of like, local classes and lambdas and stuff, but it's still not first class in that sense. But languages like Python never gave it up. But there's some really interesting ideas. What if we go the next step? Because the observation was made in this section called hierarchical program structures. So what we've discovered is that a block can hold behavior, and it can hold data, and it can hold code that runs. That's a really interesting idea. I wonder if we can do anything with that. A procedure which is capable of giving rise to block instances which survive its call will be known as a class, and the instances will be known as objects of that class. It turns out that object orientation grew out of block structure. What they are describing, Ulla Johan Dahl is one of the co-inventors with Kristen Nygaard of, and for all the Norwegians out there, I'm really sorry I'm not pronouncing it right, but it's the best I can do today. Simula 67. The language that we're dealing with here is actually Simula 67. Their ideas come from a previous language, Simula 1, which was 1965. They took Algol 60 and extended it. They wanted to deal with simulations, and they found that procedures were the wrong ingredient, the algorithmic stuff. They didn't want to think about simulations in terms of algorithms. They wanted to think about simulations in terms of things, classes of things. Well, let's change the word thing to object. That sounds a little more technical. And they didn't bolt something onto the language. They took a thing that was already there. If I've got a block, normally what happens in a block structured piece of code, the way you have instinctively thought about it, is I enter at the beginning of the block, variables happen. If I've got procedures get defined, and then the code happens. Yeah, we can mix the order of these up depending on the language, but we're allowed to do that. And then when we leave the block, that is a stack frame. It pops, it disappears, we're done. But what if it didn't? What if the block instance, this unity of data and action, survived, and you give it identity and point to it and pass it around? Hey, here's the thing. It's got stuff in it and it can do stuff. Could that give rise to a new paradigm? Well, yeah, actually, it turns out it does. So we take the code that I had before and I just add the class keyword in front, and there's no concept of constructor here. The original idea, which is actually somewhat simpler, I have to admit, than many of the things that we find in our current languages, is this idea of I initialize a class as if a function, I pass something in, that data is always available, it's immediately part of the state. And here is what would historically be called constructor code that runs at the end. Once we reach the end of this block, we now have a surviving block instance that we can now refer to, and we can pass it around. So it's a persistent block, not a block that evaporates when you leave the function. This is a really profound idea. And then we get this idea, a call of a class generates a new object of that class. Boom, object orientation is a version, object orientation and proceduralism have a really close relationship. But there's something else going on here. So you may think, well, hang on. That's interesting, because what you're describing there, Kevlin, is a closure. You have got something that captures its surrounding context. That's interesting, because I'm going to use JavaScript, because hey, why the hell not? Because JavaScript actually has inside it actually has a really elegant object model. I mean, it has half a dozen object models, just in case you don't like the really elegant one. But the really elegant one doesn't use the word class, and it's not based on function prototypes, a function prototype model. Really simple idea. I'm going to use lambdas. And this idea of lambdas and closures is a really intimate one. But many people think, oh, lambdas, you must be doing functional programming. Lambdas aren't unique to functional programming. Lambdas are unique to programming. You'll actually find lambdas and the concept specifically applied of closures is fundamental to many paradigms. It's not distinct to functional programming. Indeed, there are many functional programs that don't actually do lambdas either at all or very well, because the principal unit of composition is the function. It's not necessarily the freestanding function, it is the function. Clearly, for many people, they think, again, this is one of those ones that, just like I mistakenly and many others have mistaken the concept of data abstraction as being unique to objects, so the first time you encounter it, you go, hey, this is object orientation. It might well be abstract data types. It might be one of the other modular approaches. The same thing I notice among a lot of programmers, because many of the programming languages these days have been saying, hey, guess what? We've added lambdas. So C++ added lambdas in 2011, Java added it in 2014, and everybody's been adding them. JavaScript's sitting there going like, please, we've been doing this since the 20th century. It's the mid-1990s. It had lambdas in there. It might not have had the arrow notation, but it had lambdas. That was part of the inspiration for it. But that idea is, for many people, they go, oh, I'm now doing functional programming. No, you're not. You're just programming with lambdas. Functional programming is a lot more than lambdas. Some of these languages that are acquiring lambdas, that you can be a little more functional in them, but you're not necessarily doing functional programming. If you're a Java programmer, that is a language that will never be functional because you can't define a function, a freestanding function in it. Until you can, we can't consider it functional. But you can do lambda-y things and more functional things. That's certainly true. But there's a purity here that allows us to get inside the essence of the object model. So we've understood the object model from proceduralism. Let's understand where it comes from here. What I've got is so I'm going to do everything with lambdas. I'm going to have a function called new stack, or rather I'm going to have a name that I'm going to bind to a lambda that when executed, this is a block. There is state in this block. It's a list called items, and then I'm going to return a Cartesian product or object or dictionary, however you want to look at it. And this contains lambdas that refer to this private state. This is the ultimate in private. It's not a keyword that says private that I can inspect or hack using reflection. It is the ultimate in private. This is a local variable. There is no way from the outside to get into it. What I'm offering the outside world, and this actually starts taking us into territory that for those of you who are old enough to show the scars, looks more like Microsoft Com than anything, which is actually, bizarrely enough, a pure object model. I'm going to offer you an interface. Here's a set of functions, or here's a set of names that bind to lambdas that then further refer to private state. You don't get to look at that state. There's no types here. I'll come back to types later, but it is a very pure object model. It's purely based on name. The data is fully abstracted. I can switch my implementation around. Here I'm taking the head of the stack is at 0, and here it's back to front. So there's this really interesting idea about this unity of ideas, which was observed by William Cook in a paper in 2009, where he revisited a paper from 1984 by Cardelli and Wegner, and that's the same Cardelli as Abadi and Cardelli, who wrote A Theory of Objects. William Cook wrote this paper on understanding data abstraction revisited. There's a bunch of interesting stuff there. He gave a talk on it as well. But he makes this wonderful observation: lambda calculus was the first object-oriented language. So it's a case like, whoa, okay. So a lot of people think, oh, yeah, my language has just got lambdas, 21st century. JavaScript is feeling a little bit smug because it got its lambdas in 1995. Lisp is feeling even more smug because in 1960, the first implementation of Lisp, that had lambdas. But actually lambdas, that's the work of Alonzo Church. That dates back to 1932. So basically, if you've been getting excited about lambdas, welcome to the 1930s, programming like it's the first half of the last century. This is the original paper. He explored this idea. He did not create lambdas because he cared about programming. Programming was not a thing. He cared about it because he was trying to explore certain concepts in mathematics. And the 1930s were a very challenging time, well, for the world, but also for mathematics. Kurt Gödel in 1930 had just published his incompleteness theorems, which kind of messed up everybody's idea that maths is complete and elegant and consistent. And so there were a whole load of things that came out of that, including one that's probably more applicable to us, the halting problem, as well as some other ideas that came out of that, type theory. But he was exploring this, so he created a simple formalism. And the better known paper is the 1936 paper. And so I will claim to have read the words on these, but not necessarily fully understanding all of the consequences. I'm not a mathematician by training. I used to deal with the real world, physics, and then I decided to escape the real world and go into software. So I've carefully avoided having to know this stuff, mostly. But we can create an abbreviation. I'm going to create a stack using pure lambda calculus. I'm going to equate the name new with a lambda taking 2 parameters that yields a second one. That's an arbitrary decision. I could do it any way I wanted, but that is my decision to create a new stack. Push is a little more fun. We're going to take 3 elements, one of which is going to be a stack, one of which is going to be a new element, and we're going to bind them together. This is actually a form of data abstraction. We're going to, it turns out that lambdas are all about doing stuff. There's no such thing as a typed lambda in the original model. There's only lambdas. So we can do this, and I can create a formalism for pop, and I can create a formalism for top. This is all good fun. I'm not going to linger on this. I have a different talk where I talk about actually lambda calculus and how it surprises us, where I explore this in more detail. But there you go. That's a lambda version of stack. If you want the purest version that you could possibly get. Let's pick up another aspect of this stuff. Object orientation. Concatenation. Now, you might not be familiar with the term, but that's what we call inheritance or derivation. Concatenation is an operation defined between 2 classes A and B, or a class A and a block C. What's really interesting is the purity of Simula is it allowed you to basically say, well, it's all blocks. I can now actually have a block inherit from a class, or as it were, extend or concatenate a class. And I can have blocks. It's a very cool kind of relationship. So what is a concatenation? It consists in merging of the attributes of both components, the base and the derived, and the composition of their actions. Okay, that's kind of extending and overriding. We can actually do that with our nice little faked object model. Again, we don't actually need classes. This is a purely object-based model. I can define the concept of stackable. Okay, I'm going to define it by capability, a mixin. I'm going to say a stackable is basically I take a base and I take whatever base class we want, and what I'm going to do is I am going to add some operations to that and some state. And that's what the assign operation here does. And so to get the stack that I had before, I can simply say a new stack is now equivalent to a stackable against an empty set of operations, an empty object. Okay, take an empty object and now add stackability capability to it. I'm also going to add another capability, clearable. The thing that is clearable, when you call clear on it, empties out. So now I've decided my new stack is a clearable, stackable concept. So I'm doing composition here. In fact, yeah, function composition. So here we have some functional looking code. So I've just defined inheritance in terms of what many people think of as being a functional programming concept, reduction or folding. We've got that. I'm using function composition to define data abstraction and composition. There's a kind of unity here that's quite intriguing. It also makes us think, how do we use this mechanism? Because this is the people got very excited, incorrectly. Reuse. I can reuse everything by inheriting. There are whole books dedicated to this. Bertram Meyer's Object-Oriented Software Construction, a book of 30 years ago. People keep referring to this book, but very few people have actually read it. And because I was running a workshop just beforehand where I corrected somebody on their incorrect use of the open-closed principle. So if you are familiar with the open-closed principle that is popularized by Robert Martin, that's wrong. Robert Martin did not correctly read the book he borrowed it from. This is the original source, Object-Oriented Software Construction by Bertram Meyer. In that, you discover what it really is. It's not at all what Robert Martin thinks. So if you think you are using the open-closed principle in your code, have a chat with me afterwards. It's all based on a big misunderstanding, but he seems to have made a certain profit out of it, so he's not going to change his understanding. But open-closed principle is not what people think it is. Also, Bertram Meyer's advice was pretty much inherit from everything. Multiple inheritance is good. Let us inherit from everything we want to reuse. This is terrible, and we already knew this was a bad idea back in 1972, because we see here that Dahl and Hall were very clear concept hierarchies. The construction principle involved for using concatenation is best called abstraction. We concentrate on features common to many phenomena, and we abstract away features too far removed from the conceptual level at which we are working. This is 72. We also have a much better formalism. This one is not always correctly understood, but it is better understood. Same Barbara Liskov substitution principle. This is her 1987 paper. A type hierarchy is composed of subtypes and supertypes. Many people have taken this to be the organizing discipline for a good class hierarchy in object orientation. But she's actually not really talking about objects in that sense, or classes. She is talking about types. The intuitive idea of a subtype is one whose objects provide all the behavior of objects of another type, supertype, plus something extra. What is wanted here is something like the following substitution property. And honestly, if you've just been eating carbs for lunch, you're going to fall asleep in the next sentence. If for each object O1 of type S, there is an object O2 of type T, such that for all programs P defined in terms of T, the behavior of P is unchanged. When O1 is substituted for O2, then S is a subtype of T. It's like, oh man, okay. I can actually, the great thing about the Liskov substitution principle, the term LSP was coined by Jim Kaplan in his Advanced C++ Programming Styles and Idioms book in 1992, based on Liskov's paper. She did not vainly name it after herself, but Cope extracted that observation, which is why it gets associated in part with objects. But we can actually do that here. So I'm going to add a new mix in, a non-duplicate top. If you mix this in with a stack, what it means is that when you try and push onto the top something that is already there, then it's going to ignore it. So now I've already got that at the top. Okay, so this is an interesting idea. Now what I'm going to do is I'm going to write a test. Okay, I've got a set of tests here in an ad hoc testing framework. I've got a test here that says a non-empty stack becomes deeper by retaining a pushed item as its top. And then I've got the test body. I've got a new stack. I push NDC, I push TechTown, I push TechTown. The stack depth is 3 and the top is TechTown. Now, just as a clarification, if you're not used to JavaScript, in JavaScript, if you want something to be really equal to something, you just hold down your finger down on the equals key. The more equal you want it to be, the more equals you need. But this is like really equal. 3 equals is like, yeah, I mean it. So that seems to be the invariant. Okay. When I do this and I compose, I have my conventional stack that has clearing operations and things like that, then the test passes. When I also mix in a non-duplicate top, the test fails because we tried to push TechTown onto it twice and it ignored the second one because it's a non-duplicate top. Therefore, depth is 2 rather than 3 and the test fails. That's the key idea. LSP is actually a testable proposition. We are saying that if I have something that says it's the same type, then it should pass the same tests if it conforms to that. If it does not, then it's not the same type or our tests have made too much of an implementation assumption. So this is actually a testable concept. But there's another idea here. Barbara Liskov wasn't really talking about objects and classes the way we understand them. She was actually talking about abstract data types. She was talking about the substitutability. She wasn't talking about plugin frameworks. She was talking about the idea that if I have a program that is linked with respect to one implementation of a type, if I substitute an alternative implementation, then that program should have the same behavior identically. She says the behavior of P, the program, is unchanged when O1 is substituted for O2. That basically means if you say, I'm going to have the same behavior but add logging, then you've broken LSP because the program no longer has the same behavior. It now does logging as well. So the strict Liskov substitution really is quite strict. It really is about the data types and the privacy of that. But we do nonetheless have a general principle we can learn from it, even if we're not going to be so strict. And it was captured back in the early 90s in the Gang of Four book, program to an interface, not an implementation. Now, that doesn't mean use the interface construct in the programming language that you're working in. Although that's good. What it means is if there's something that has a public aspect and a non-public aspect, you depend on that and you organize your code accordingly. It's really about the shape of the thing. And that, if we look at this from a TypeScript point of view, I can characterize, I can say, this is what you can depend on. Interface stack. If you have a thing and it claims to be a stack, then it should support depth that returns a number. Top can return anything. Pop doesn't return anything. And a push takes anything and returns void. And I can take that previous JavaScript and actually make that claim. That's why this is interesting, is because this doesn't use the conventional class construct of JavaScript, but it still satisfies the types. Now that causes us to revisit the kind of the big three of object orientation. The way that many people have been taught them, particularly if they've come through the kind of C++, Java, C# route, is the big three are encapsulation, inheritance, and polymorphism. what we actually learn, and particularly if you work with dynamic languages, is actually inheritance really isn't that interesting. The big deal is polymorphism. In languages that have a static type system, inheritance is, its main use of inheritance is for type conformance. It's not that important. You use inheritance to get polymorphism. If I can get polymorphism another way, I will get it another way as well. So in other words, inheritance in a statically typed language is an enabler for polymorphism. Therefore, it's subordinate to it. The real criteria here is the polymorphism idea. And that's important when we look back at this. I can equally well have a piece of code that expects stack and have a completely different implementation written using the conventional class construct that we find in TypeScript, and it will still satisfy it. It is to do with conformance to an interface. Whether we have a derivation from it or not is a question of type system, but it is not fundamental to the paradigm. People have been mistaking their type system for the paradigm. I get this a lot with when people sort of say functional programming. What a lot of people who talk about functional programming actually mean is Hindley-Milner type system, which excludes a number of functional languages such as Clojure, which doesn't have such a type system. Often people are focusing on that one thing and they take it to be the whole. And we see that this has been happening all through history. This is often how we approach paradigms when we're new to them. And if we actually think about it more clearly, what we've really got there is encapsulation is the strongest point. Encapsulation is the dominant aspect, followed by polymorphism. Inheritance is less interesting or important. Because when we think about it, the idea of programming to an interface, why am I programming to an interface? Because I'm hiding the implementation. So in other words, it turns out class hierarchies, when constructed in a Liskov style, class hierarchies are an example of encapsulation because you no longer depend on the implementation detail, the concrete class. That's irrelevant. Well, isn't that encapsulation? Well, yes. If you like, it's a dynamic extension of the concept of encapsulation. A good class hierarchy is an encapsulation. My favorite observation